We went everywhere in the solar system. We have a little more than 250 probes that have been sent out to explore the solar system. People often say that Earth's twin planet is Mars. Well, no, not at all. It's Venus. Give a geochemist, I'm using myself as an example, 10 milligrams of a rock. He will tell you the history of the planet. When we talk about exploring the solar system, but at 11.2 kilometers per second, you don't make money. No one has ever made a dime from exploration.
Hello, Sylvester Maurice.
Hello?
We're happy to welcome you to the show. Could you introduce yourself for those unfamiliar with you?
I'm an astrophysicist specializing in planets, a planetologist at the Institute for Research in Astrophysics and Planetology. It's a large astrophysics lab in Toulouse that combines a university, the National Center for Scientific Research, and the National Center for Space Studies.
So planetology, how does it work? What does it involve?
Well, when we talk about astronomy, it's about all celestial bodies, and Earth, by the way, could be included. And planets are really the bodies that orbit around the sun. In Greek, I think it means wandering star. In a starry sky, you have fixed stars on the sphere. Earth's rotation causes constellations to appear to move, but some points shift position from night to night. Right now, for example, we can see Jupiter very, very clearly. You can't miss Jupiter. So the famous planets. So in all the branches of astronomy, I'm one of those who it's really like the backyard, the neighbors, very, very close.
Yeah.
By the way, that's a big advantage. It's so close that we can go there. We can send either astronauts, why not, or more often robotic missions. While my friends who study stars, galaxies, black holes, or cosmology have to rely only on photons and gravitational waves. They're their messengers, while we can be the solar system's messengers.
Okay, it is truly a fascinating topic. How did you come to this subject? What made you want to study planets?
Well, I was lucky. For me, it was a calling from a young age, but above all, it was a calling for science. It was the scientific approach that fascinated me. Physics and chemistry are really the core and foundation of what we do, while math is more of a tool. So I became an engineer, and then I did a Doctor of Philosophy in Astrophysics. That's a pretty classic path. And more focused on planets, because I also liked machines, robots, and technology. And we're lucky to be able to do it. Maybe astronauts too, who fascinate us all a bit as that embodiment. And so that's the path that very fortunately led me to the solar system.
All right, so among the different planets, which one caught your attention first?
That's a good question. I started my thesis on Saturn, beautiful Saturn, fascinating with its rings, about 50 moons, its mysterious moon, Titan. So that's how I started. We were preparing a mission called Cassini at the time.
In what year?
The 90s. And then I was lucky enough to start with Saturn. When you work on Saturn, you also take a look at its neighbor Jupiter. So I worked a bit on Jupiter and a little on Neptune. That was when we studied data from the Voyager and Pioneer missions, the first exploration missions. And that fascinated me. And then, it's often because of an encounter and so on. Someone said to me, hey, we've got something here. We don't really understand it. Well, it was the moon. And so I ended up studying the moon for quite a few years. By the way, I think it's still my planet. Well, whether we call it a planet or not, it's quite fascinating. And then, after the moon, I went toward Mars, a bit toward Mercury, then back to Mars. We travel in the solar system. That's our thing.
A little journey through the solar system. So you said the very first planet you studied was
Saturn.
So how can we study a planet that we can't land on yet?
Exactly. We're explorers. We investigate unknown worlds, but these are truly unknown, They're not just themes. And above all, we're observers. What really matters in our work is the data, not your idea about an object, like thinking you know what it's like. What's important is to take a piece of data. The data is what matters. So at the time we had the first emission data, Pioneer 10 and 11, Voyager 1, Voyager 2, which were the first missions going to the giant planets. I was told, here, take the Voyager data and tell us more about Saturn's magnetic field. So the question was to understand Saturn's magnetic field. I was looking at the data. There were measurements of magnetics, measurements of electrons, of protons. I made small models. That's what a Doctor of Philosophy student does. They have 3 years to focus on their project. Not impressive, my thesis, now that I look back. By the way, at one point I was with my thesis advisor, an extraordinary person, and we could clearly see that there was a signature that was strange. And I think we missed the greatest discovery. It was water, and we didn't realize it. It turns out that there was one of Saturn's satellites called Enceladus, which orbits around it, and there's a geyser that spreads water throughout the whole system. I can tell you I began by missing what could have been a great discovery. So we study a planet, and like we do with all the young people who often start out, it's the data. You know, we give them a set of data. You dig in, you turn all of that over in every direction. You look at what makes sense, what doesn't make sense, what the different sensors are telling you. What new things can we learn? That's often how we start.
All right, so with all this data, the goal is to spot those patterns that are a bit out of the ordinary, that are unexpected?
Now, that's a good question. It's actually in a data set. You have a data set. You're given spectra. It could be temporal measurements, a temperature that fluctuates, and so on. And already you say, well, what is an instrumental bias? Because the instruments, they respond as best they can sometimes. Sometimes they get too hot themselves, so they don't respond well. Sometimes there are communication problems. And then after that, the signal, often it might be the average signal that we're looking at. It's often the variations. You said it well. It's what stands out. You see a pattern, then occasionally 2 points do this, and maybe that day the temperature wasn't working, which could be an operational bias, or there may be a real signature. That's going to be the whole thing, the challenge, trying to find data. Now, we call it data mining or data science. Those are the English terms, trying to find something that makes sense. We all code, but back then the language wasn't Python. It is now. And almost everyone starts like that. A few will start with theory, but that's pretty rare. A few, the very young ones, start with theory, but you have to be extremely good. You can do it in some fields like cosmology for theory, and others will. We generally turn this data into models through modeling. So the model showed me what the magnetic field of Saturn looked like. And what I take away from all this, and what I try to explain to young people now, is that the fundamental thing is the data. That's why our profession is built around what we call observation services. We observe, we collect, and then we try to interpret.
All right, so to collect this data, we sent out different probes. What are the different techniques for collecting this data?
First, you need a probe, you're right, and sending one into the solar system isn't easy. We'll discuss that further, but you also need a powerful rocket. I'm often asked when solar system exploration begins. It's not a distance, but it's a speed. If you manage to launch your rocket, and then with a speed that allows you to orbit the Earth at 8 kilometers per second, then you're in orbit. At 9, you're higher. At 10, even higher. Then, if you manage to launch at 11.2 kilometers per second, you leave the Earth. So actually, the exploration of the solar system begins at 11.2 kilometers per second. That's called escape velocity. You could go at 16, sorry. When you escape from the Earth, you fall into the gravitational potential of the sun. You are now around the sun. If you exceed 16.7 kilometers per second, you can escape the sun. And then you go somewhere else very slowly, but you do go. And so it's first a speed. So this speed is given to small robotic probes. Very few, there aren't many of them. I did a calculation. We have a little over 250 probes that have been sent to explore the solar system. 250 since the year 57. That's very few, just a few percent. Right, most of the probes, they stay around the Earth. Even astronaut missions are much more numerous than we are, so that's very few probes. The first ones, they were called Pioneers, Voyagers, Vikings. We had some on the moon. They were called Luna for the Soviets, the explorers. So there was a whole range. There are still only about 250 nearly half-headed for the moon, so that's not many. It's about a dozen, for example, for the giant planets. So not many probes. These are quite complex objects, very complex. Not necessarily at the cutting edge of technology. They're mainly robust. energy sources that are solar panels or nuclear reactors, well, reactors that we call isotopic. Plutonium generates heat, then electricity. So fairly autonomous probes, but not necessarily very smart. First, we want them to get the job done. And that's an important point, because often young people come to me and say, I want to work in space. It's cutting edge technology. No, no, no. If you want cutting edge technology, you'll work on phones. Space is about robust technology. It has to last. It has to hold up. It's ultra vacuum. It's vacuums that are even better than what we can simulate in the lab. There are radiations, cosmic radiations, particle radiations. It's cold or hot, depending on where you look. At launch, you feel vibrations and shocks. So it's robust technology. And inside, we make instruments. Now, the instruments often represent 10 to 20% of the vehicle's mass. The vehicle's primary function is survival. Provide electricity to everyone, communicate with Earth. If it doesn't communicate with Earth, it's useless. So that's what we call the support systems. And you have 10, 20% instruments. So over time, we've built quite a variety of instrument families, which are generally instruments that we have in our laboratories. They're not any smarter, and in fact, they're even less so. In your lab, you have instrument the size of this room, and you're told to take it to the moon. It's only 5 kilos. It's less efficient. On the other hand, it's in situ. In situ missions aren't just technological fantasies. It's robust, solid, well-designed, optimized. It's not about performance overkill. It's not as good, and we'll come back to that. That's why we want samples in our labs, because we can do better in the lab. What we can do on site isn't as good, but it's still there. You're 1 billion, 100 or 380,000 kilometers away, far away on site, and must make do with what's in our labs. A lot of cameras, so we like cameras, whether it's visible, but it can be ultraviolet, it can be infrared. And then we could go as far as all the photons, X-rays, gamma rays, so mainly cameras, photons. And then a lot of chemistry instruments too, quite a few instruments that measure chemical compositions or how the atoms are connected to each other. That's called mineralogy, for example. We have instruments like particle detectors. They're called plasma instruments, for example. There are electrons, protons between the sun, and for example, between the sun and Jupiter, we could do that, or around Jupiter. Measurements of fields, electric fields, magnetic fields. So we have different categories, and some of them are pretty cool. I think the most original of all is one of the latest ones we made for Mars. It's a microphone. Now that's rare because you need an atmosphere, and there aren't many places with one. In the end, these are pretty common instruments. We don't necessarily invent them. We take them from Earth, and we have a word for that. We space qualify them.
Okay.
I mean, it's pretty rare that we invent something specifically for space. Usually we take it and then we bring it all the way to the edges of the solar system. So you see, when I said that, it's because it's both a scientific profession. Science is about what ideas we have about objects, their origin, their future. And it's also a world of technology because we have to develop technology. That's why we're very close to space agencies, for example, or large companies, or even small companies. There are companies of all sizes. We need technology to explore the solar system.
Okay, so do you ever place so-called orders, meaning do you communicate your needs to companies to create custom tools?
Typically, that's how it works worldwide. There are only 6 major space agencies, making it simple. Historically, the Soviet Space Agency was first, later becoming Russian Roscosmos, then NASA, and then Europe, which formed European Space Agency, and then 3 more emerged later: India, Japan, JAXA, and China National Space Administration. That's about it, more or less. That means there isn't someone just doing small operations. At least those 6, they can build a rocket, run a mission, and make the instruments inside.
Okay.
That doesn't stop a country, Brazil and so on, from being able to make an instrument that we can put on another probe. That doesn't stop Iran, Israel, Afghanistan, Korea for other reasons. Knowing how to launch rockets. There's a whole geopolitical world, it's complicated. But basically, among the 6 major nations that I mentioned, agencies typically build the vehicles which supply electricity, communicate with Earth, and handle thermal control. Usually agencies make them, but they can have an industrial company do it. For us, there are 2 major ones in Europe, what we call the primes, Airbus Defence and Space and Thales Alenia Space, which are in the process of merging. but they make the vehicles. NASA does the same, asking Lockheed, asking Boeing to make the vehicles. What's quite interesting in the scientific world is that these major agencies ask academic laboratories to make the instruments. So it's us who make our instruments. That's quite interesting. That is, they say, since you're asking the questions and you know your instruments, make them. You'll have your data, you'll analyze it. That's how the system works. And even in China, where it's a little different, they adopt this model. We turn to academia, mainly the local university and the National Center for Scientific Research in France. The Germans, it's a bit different, but well, it's pretty much the same. It's the same model. And so we make our instruments, but we don't make the vehicle. Americans are currently trying to create something new called new space by having private companies make the instruments or vehicles. The setup changes slightly, but the result is always the same. Because we must not forget that when we talk about exploring the solar system at 11.2 kilometers per second, you don't make any money. Exploration has never made anyone money. Why? Because we create something, it's knowledge, and thank you for spreading it. We don't sell it, we give it to you, right? It lets you create beautiful magazines, especially with royalty-free space images. Since you've already paid for them through taxes, you won't be charged again. Currently, Americans are trying to change the model by suggesting we could buy exploration data. It's all a bit complicated, but basically we create knowledge, we give it away since it's already been paid for by taxes, so we spend money, we don't make any, right? So it's not exploration, especially in planetology, that's going to attract industrial crowds. Industrial companies participate because we fund them to build probes or collaborate on instruments. Sometimes they create instruments due to their expertise, but it's still a public or almost public contract, right? And so in the end, well, laboratories like ours, we're lucky in Toulouse, or there are some in Paris. The laboratories can be in France, in Marseille, in Bordeaux, in Lyon. We've distributed our laboratories all over. We build our instruments. And so one person is a specialist in making cameras. We focused on laser instruments in Toulouse, while ultraviolet spectrographs could be made in Paris and infrared ones in Orsay. We build our instruments, which is why our laboratories have researchers. Researchers are normally supposed to say, here is the question I'm asking myself. What is the origin of the moon, for example? Here is the kind of instrument I need to answer my question. Then they turn to the engineers in our lab, where we have many engineers and technicians, especially one with many ideas. In general, the researcher's role is to have ideas. That won't lead anywhere if there's not an engineer who knows how to do it. In our labs, we value the engineering that makes things happen. Someone understands what the researcher needs, the type of measurement required, and envisions what the instrument could be. Mechanics, opticians, electronics engineers, and computer scientists all collaborate as a team. The agency provides the money because, of course, the project needs to be funded. After a while, they say, hey, we've designed this, an electronic board. Well, let's call a manufacturer and say, now you can make it. We're not going to make everything ourselves. For us, it's the design that matters. Then, when they've made all the parts, we do the integration. So we have people who handle the integration. They're small instruments, but they're really dense. We've packed everything possible inside, since mass is often crucial. And at that point, well, we do the assembly, the integration, the tests, and then we deliver. During that time, usually the vehicle has been built. It could be NASA that built it. Recently, we did a mission with the Chinese. They made the probe, so that was nice. It was to go on the moon. It was a mission called Chang'e 6. If I may say, the Chinese have done an absolutely remarkable job in recent years. They've caught up on a huge gap so quickly. At one time, we thought we would teach them something, but now we know that it's us who have to learn from them. They've completed 6 successful moon missions. The first 2, Chang'e 1 and Chang'e 2, were orbiters. Chang'e 3 and 4 were landers with small rovers. You know, U2, the little rabbit, as they say. There's one on the far side and there's one on the near side. Impressive, right? And then after that, they did Chang'e 5. Chang'e 5 landed and brought back a sample return, which is a bit like what the Soviets did with the lunar missions. And last year, in 2024, they did a sample return mission on the far side.
Okay.
That was the Chang'e 6 mission. On the South Pole side, we believe there's a deep crater called South Pole Aitken. It is huge impact basin, so deep we believe we've reached the mantle. It's the largest impact basin in the solar system. There are many impacts, but this one tops them all and is on the other side. They landed there and later asked France if they wanted to add an instrument. And so our laboratory built a radon measuring instrument because we wanted to know. Radon is an indicator, since it's a gas with a radioactive component that allows us to tell if the ground is cracked, how the material comes out. So we built it in our lab, we made it, and then at some point we delivered it. So we went to China with our instrument. We mounted it on the vehicle, sent it to the moon, landed it, and started it up. So they are. After just over 24 hours, it stopped because the vehicle was returning to Earth. And we're still over there. Usually our vehicles never come back. It's rare. It's rare. What comes back are just a few samples. So that's it. That's the system. That's how we operate. So we're obviously very close to the agencies because we need the agencies to manage the whole system. We're close to manufacturers since they build the vehicles. We have our own expertise, and we also connect with politicians. Because when I say we're spending money, we need to convince the politicians. We're close to the media because we need you as messengers. Our system ends when people stop mentioning us. Why? We all know that space is appealing, and I think you experience this with your magazines and with what you produce. I hope that those who watch your videos leave you good comments saying, space is appealing, we can see that, but it's only appealing because we talk about it.
Yeah.
We're afraid you'll stop mentioning us. Please don't. Talking about us helps make the system more virtuous. Politicians show interest, saying these people are costly but valuable because they answer questions. So the goal isn't to do just anything. Right now it's getting a bit out of hand. It feels like it's getting out of hand, but we need to keep asking ourselves good questions, big questions. If I take the moon, well, what's the origin of the moon? The moon is a piece of the Earth. We had to imagine a story 4.56 billion years ago. That's really amazing. Or at one point, there's an impact from a planet called Theia on the Earth, which then creates the moon, or maybe on another planet. I look at Mars and I wonder, was there ever life on Mars? The famous Martians, did they ever exist? So I think these are fundamental questions. It's about our origins in general, the origin of life, the origin of worlds. But we could not ask ourselves these questions. One day a politician could say, no, your thing is really interesting, but we can't afford it anymore. Stop. We could. There will just be a few hundreds of us in the street shouting, don't forget us. You'll take up our cause, I'm sure, but we could not do it. If we do it, it's a political choice. Planetology involves science, technology, and politics, and then a bit of dreaming. And a part of it, I don't know if you want to go there, of planetology is we send probes. We've gone as far as Pluto. We've gone everywhere in the solar system, from the closest, Mercury. We've gone a lot to the moon. For the most part, more than 100 probes, about 30 to Venus, around Venus, on the surface of Venus, about 50 around and on the surface of Mars, roughly 10 for giant planets, a dozen for asteroids and comets. We've explored everywhere. Sometimes we've landed, other times we've stayed in orbit, and sometimes we've just flown right by. We've really made quite a lot of progress. Sometimes we've even flown. When we fly a Genuity on Mars, we're like, oh yeah, we've really done some things. Sometimes we've come back. That means we've brought back samples. It could be the moon, samples from the moon. It could be asteroids. We have samples from asteroids. We have quite a few missions. For example, the asteroid Bennu, or that's an American mission called OSIRIS-REx, or the Hayabusa missions, which went twice, Japanese missions that brought back samples. One day, maybe we'll bring back Mars samples, though Trump canceled that plan. We'll discuss it later, but we hope for Mars samples. So we came back, and then sometimes we send something a bit better, a bit more advanced than a robot, meaning astronauts. That, as you know, is for the moon up until now.
By the way, so for now, we don't have any samples from Mars. So how did we manage to analyze the soil and come to so many conclusions?
Well, with a lot of effort and a lot of time. So we're very lucky. We've just lived through a kind of amazing era. In the past 25 years, we've had over 20 missions to Mars, which is important because it relates to the fundamental question of life's origin. You know that. I'll explain it to you very quickly. Earth and Mars formed together 4.56 billion years ago. Early events like the formation of a moon were significant. And then the Earth cools down very quickly because at first it's a big ball of impact since it grows through successive impacts. So it's basically a ball of magma. That's called accretion. Earth forms, cools, and the atmosphere appears quickly. In less than 200 million years, there is water, the oceans, and then the Earth keeps its system, and we still have it today. Mars begins in the same way. There is a dense atmosphere, there is water, liquid on the surface. It's a bit less than on Earth, but there is some. Suddenly, after 1 billion years, everything stops as it loses its atmosphere and becomes trapped in its past. Why is this interesting? It's because Earth has no memory. Earth hasn't kept anything from that ancient time. Why? Because it has tectonics and an ocean floor. After 300 million years, everything is redone. Tectonics works quickly. Or there's water erosion, wind erosion, and erosion from the biosphere itself. Ultimately, Earth is a planet without memory. You find a rock and people claim it's 200 million years old, but asking for a billion-year-old rock is more complicated. We know where to locate them. Give me one that's 2, give me one that's 4. We won't find it there. We'll find a little mineral phase, a zircon at the bottom of something. Earth lacks memory, but Mars, having frozen in its past, retains one. So in the end, it's a kind of snapshot of what the Earth might have been like in its first billion years at the time when life was appearing. That's why Mars is so fascinating to us. It's an answer we can't find on Earth, so we look for it on Mars. How does life appear? The problem of habitability, organic chemistry, accretion. So for that, we've sent lots of probes. We start with orbiters, that's easier. Then we go down, we put landers, like Vikings, for example. Then we put rovers that drive around, and we can even fly one. So we've done that with lots of instruments, and we in Toulouse were lucky enough to build instruments that we share. We accomplished this with the Parisians, our friends, and with Bordeaux and Lyon, everyone together. We make instruments. And one we really like is ChemCam on Curiosity. It's been 12 years. It has a small laser that heats rocks to 8,000 degrees when fired. So we developed a laser. Why? Because in France, we're the champions of lasers. And there was a manufacturer who was able to make this laser, so we approached them. We asked if they could make our 20-kilo laser weigh just 1 kilo to use on Mars, and they agreed. After years of work with Thales laser, we now have a laser that fires daily on Mars, producing a small light through a telescope. We're 2 or 3 meters away, we observe the light, then analyze emissions. It shows us how much calcium, potassium, sodium, oxygen, iron, and even strontium are present. I remember the first spectrum, we were so happy then. We've just passed 1 million spectra, so this thing has been running for 12 years. That's how we study the planet. We have 1 million spectra of rocks. This rock has more sodium, while that one oddly has more manganese. So then you wonder, why is there manganese? So we build these instruments, they're on Mars, and we also have some really great instruments. We have another one that was made here, chromatograph columns that were made in Paris. We take some material, we put it in our device, we have a small oven, we heat it up just like we would in the lab. We do gas chromatography, and we look at the molecules. That's how we detected the first organic molecules. These are, once again, instruments that we find in our labs that we brought over there. That's great. We're doing an amazing job. One day I went to give a seminar. I think it was at a normal school in Lyon. The researcher said, "What you're doing is great, but it feels like 19th century science. It hurts, right?" He wasn't wrong. That is to say, what we're doing is a level of precision that wouldn't make sense on Earth. On Earth, we do 10 times, 100 times, 1,000 times better, whereas on Mars, we're talking in percentages, or at best in ppb, parts per billion. On Earth, we do PPT 1,000 times better. Actually, it's science as we can do it. And that's why on this big Martian question of whether there was ever life on Mars, we think we'll have trouble answering that in situ. We'd need to bring back a sample, and we've been asked to do that for 30 years. We hold prospective seminars, so in perspective, it's about your vision for 10, 20, 30 years from now. We always say the same thing. We say we want samples. We want a piece of Mars in the laboratory, so we really need to bring one back. And well, We've seen this with the moon. It's often called the Rosetta Stone of the solar system because we frequently refer to it all the time. Our reference is the moon, especially regarding the history of timing. We've counted all the craters and, using the samples brought back, created a sort of timeline. And one of the examples from the moon was to say that giving a geochemist, well, this is my example, a geochemist 10 milligrams of a rock, he'll share the planet's history because he'll examine it so precisely. We did this with the Apollo missions, 11, 12, 14, 15, 16, and 17, bringing back 380 kilograms of samples. We haven't even reviewed all of them, as we think better instruments are leading to discoveries we couldn't have made 20 or 30 years ago. The Chinese have now brought back a few samples, a few kilos from the two missions, Chang'e 5 and Chang'e 6. The Soviets' Luna 16, 20, 24 missions returned moon samples. We realized that was how we'd progress. So with those, we've already done it, and now it's really about Mars. We need samples from Mars, though we already have Martian meteorites, which are small rocks that reached Earth by chance. You didn't know that?
So, how is it possible for a rock to leave a planet, end up on Earth, and for us to know that it's from Mars?
That's actually the second question, which might be more interesting. The first one is here. I have a projectile coming in, and bam, it makes an impact. We see a lot of impacts. We have millions. We see them often. There's a small mountain in the center because gravity makes it rise up. You see, look, everywhere in the center, there are little spots. Take the one that's shiny, Copernicus. Well, all of them, what do? They send out material. The impacts are so intense that the object is instantly vaporized by the heat and disappears. It pushes into the ground, cracks it, and ejects material. The ejected material is often so forceful it reaches escape velocity. And so each impact puts material into the solar system that ends up orbiting around the sun. An impact on Mars produces debris that falls back to Mars and some that orbits the sun. It shifts due to several factors, making it complex, but it might affect the Earth. And so in our daily rain, every day we receive meteorites. We see plenty of them. They burn up in the atmosphere. So you have shooting stars. We love shooting stars. A shooting star is like a cherry pit that burns up entering the atmosphere. But if the object isn't a cherry pit, but is the size of a plum, it won't burn up completely. It hits the ground, someone picks it up, often a farmer or peasant back then, finds a rock in the field and takes it to the Institute or Natural History Museum in Paris. They ask for analysis and are told it's a meteorite from the sky. And these can be very old objects. They're older than the ones we find on Earth. Why? Because, as I told you, we don't have a past. That's how we found, for example, objects that are 4.5 billion years old. We even found one in Tarn, the Orgay meteorite, which serves as the reference for the solar system's composition. We use it worldwide as our standard. Regarding this one, you should come see it. In Toulouse, you have to come. So we have these objects, so we analyze them, we group them into families, and we realize they're not all the same. Some come from objects that are more like the cores of asteroids that exploded, so those would be mostly iron, nickel. Some of them have compositions that are very close to what we call chondrules, the first objects formed in the solar system. Then at some point we come across the chondrules and we say, hey, this one has a strange composition, it's not like usual. To have this composition, it must have belonged to a larger body because it lost certain elements. When we look inside and find small gas bubbles, we analyze them precisely in our labs, something we can't do on site. We realize this is a composition. It's an atmosphere we know well. It's the one from Mars. And that's how we find Martian meteorites. They come from an impact. They stayed around the surface. So for us, it's a good view of what Mars is like, but we don't know where they come from on Mars. It's hard for us to know from which era. They stayed around the sun for a long time, so they were irradiated. They entered Earth. They were contaminated. Also, if it fell, was it picked up immediately or years later? We have Martian meteorites.
Which in itself is quite exceptional because the probability that one of the impact debris ends up on Earth, and we said earlier that the Earth has no memory, so that means these rocks have to be collected within a fairly precise time frame.
These are usually recent falls, but you can find many in some places. In Antarctica, if you see a rock on the ice, it fell from the sky.
Well, yes.
There are even, I think the Japanese even made a tractor that collected these things because the ice flows in the same direction and there are concentrations. and our Martian meteorite. So I have a story about a little Martian meteorite. They're called NWA. It's a family of meteorites that were found in the deserts. Likewise, you go into a sand desert. There are people whose job is to look for meteorites. Then they sell them. There are meteorite sellers. There are meteorite markets. They don't say where, like with mushroom hunting. They just mention finding it in the desert, usually somewhere in Northwest Africa. They're called NWA. We don't know where, but there's a sand field with a black rock in the middle. It's slightly burned from re-entry into the atmosphere. There are marks we call thumbprints. So they say that's good, and this is where these people are amazing. They say this one is not like the others. It could be Martian. The question is, do we have any from Venus? But we don't know Venus very well. Do we have any from the moon? Surprisingly, we don't have very much from the moon. They have it analyzed by a lab. The lab says, I'll keep 10%. You don't mind, do you? And then it becomes so valuable that even we can't buy them anymore. There was a meteorite like that. I have a story to share that connects to the astronaut story, which we haven't discussed yet. The Cité de l'Espace in Toulouse decided to buy one of these Martian meteorites because there's one that's not very expensive since it's quite big. We know it well. And we gave it as a gift. It's about this big, to Thomas Pesquet. And Thomas, he took it with him on his first flight. He took it with him in his pocket. He went around, but I don't recall how many times. 6 months later, he returned. I asked for it back, and he said it was with his luggage or coming by vehicle. Eventually, he returned it to us. So that was the story of an object, a meteorite that crossed the atmosphere of Mars, then the atmosphere of Earth to arrive here. We found and identified it. Then it left again, crossed Earth's atmosphere in the other direction, orbited the Earth, and then came back down to Earth again. Thomas and I decided to do something cool. We cut it into 3 pieces. I asked Agnes in my lab to cut it into 3 pieces. He kept one and said, I'll take it to the moon. We believe in it, go ahead. The second piece is at the Cité de l'Espace, and the third piece we attached it to the Perseverance probe, which is heading back to Mars. I think there's never been a rock with a more beautiful, more amazing story than this one. And why did we do this with Thomas? It's because we wanted to say, it's a story. It didn't affect the mass balance. These few grams from the rover, we even did science on it because we have its signature, so it serves as a calibration target for us. And for us, it was the symbol of this duality between robots and manned flights. People often ask which I prefer, but I say we don't favor either. We need both, especially for science. We need robotic flights. And then if we can bring humans for an extra dose of dreams and inspiration. Also, we make a lot of choices in science, and it's a story that really appealed to children. So you see these rocks that travel from one planet to another, and on Mars as well with Curiosity, which I mentioned earlier, and the ChemCam instrument. At one point we saw a rock a few years ago. The rock was dark, quite large, a big rock. We fired at it. The composition was fernical. We identified it as an iron meteorite, meaning we found a meteorite on Mars. We've actually found several, including chondrites, which are rocky meteorites that are tougher to spot. I often wonder if, when we bring back Mars samples, there will be a terrestrial meteorite among them. That would be funny. So that's the story of wandering rocks. But the science of meteorites is extraordinary. I'm fascinated by it. We have, cameras in France and elsewhere that watch these shooting stars passing by or these falls. And then from time to time, they hit the ground and we identify them. We go look for them because these are objects that have been, we say they are pristine, that haven't changed much. Objects that trace our origins because they stuck together. There are still some left, fortunately, not many. And then there's the fantasy of big objects that could fall, destroy us, Armageddon and all that stuff. I think it's great because it also fuels dreams, fear, Hollywood. I think it's good for our finances. Let's not kid ourselves. There's a whole story to tell. Well, often they're still very small objects, but that's how it is. Science in the end is about samples, but we prefer to go get them ourselves, choose them. That's what we're doing right now with Perseverance, rather than just letting them come to us by chance. And that's where the scientific value is a little weaker.
Does the fact that these shooting stars pass through the atmosphere at very high temperatures, does that alter them in some way?
Yes, it does alter them. Shooting stars are tiny and burn up completely, leaving nothing behind. When they're larger, they touch the ground, which is how you identify them. There's a kind of crust, though I'm no expert. You'll need to consult remarkable people. I also like it because these are museum collections. People often ask, what's the point of museums? It's used for mediation, which is your role too, but it's also helpful for us. These are real collections that we go to. We look for rocks because we've properly identified them in the museums all the time. By the way, in our teams, the Martian teams, there are staff from the museums, the Paris Museum of Natural History, or it could be from another collection. We say, hey, I need this particular composition. They say, I remember that such and such expedition in South America back in the 19th century brought back this or that rock. And a museum is a bit like a library for us. At the library, you go to look for a book. We go to look for a rock, those famous rocks that come from the sky.
Earlier, we said it would be best to choose and visit the objects ourselves. So, apart from the moon, from which we were able to bring back samples, are there any other celestial bodies or even meteorites, asteroids, from which we could have brought back samples?
Yes, this was this discipline. The Japanese have made it their specialty. They did a mission called Hayabusa 1, but their vehicle didn't work very well. It reached the surface and bounced, but caught almost nothing due to a system failure. When it returned and the box was opened, it was empty except for about a dozen tiny grains. And they did some crazy science with things that I don't even know how they did. They launched a second mission called Hayabusa 2, Ryugu. They landed, collected material, and brought it back. Everyone is studying it now. There was quite a bit from the moon. We've collected various samples, including solar wind, which is more complex. You know, there are particles between the sun and Earth. The sun has a corona, the well-known solar corona, visible during eclipses, which emits particles. A lot of hydrogen and helium in particular, but also plenty of other slightly heavier elements. A mission I liked, Genesis, was at the Lagrange point, one of two near stable spots in the three-body problem, between the Earth and the moon, so it goes there. Sorry, between the Earth and the sun, about 1 million kilometers away, it goes there, it opens up. It was aerogels, some kinds of things made of aerogels that capture all the particles. Then afterwards it closed up and then it came back to Earth. Unfortunately, when it arrived on Earth, it crashed a bit. The parachute didn't open, but it still landed in good condition. That's how we did science with the solar wind. Sample science is really important. And really, the one we miss the most is the Mars sample. We dream of having a sample from Venus. That would be incredible to have a sample, but that's even more complicated to go and get. A comet sample is interesting. What's complicated with comets is preserving the volatile part, the ice part. If I take some ice, put it somewhere and bring it back, I'll just have some water. So it's very interesting because you'll have the composition, but you won't have the crystalline form, a lot of things. So volatile samples are difficult. Rock samples are a bit simpler. So that's how we have all these samples. And actually, it's not really a bargaining chip, but it's a bit like a gift. Not long ago, we got a phone call from the French Space Agency saying, I think the President of the Republic came back from China with 2 suitcases, come and get them. And actually, it turns out that the Chinese presidency had given 2 small rocks from the Chang'e 5 mission as a gift for France. A gift, a panda or a rock. And so we did some really, really good science. Then there's an official process for responding to proposals. Today you write to NASA. Right now it's complicated, but still asking, can I have some Apollo rock? I'd like an Apollo 15 sample for this science. It's a human treasure. You request one, explain your plan and say if you'll destroy it or not. So it's a bit like there are filters. You receive it and then you do your science. In all the astrophysics labs in France, there's Luna, Apollo, Shanghai, and now there's a bit of Hayabusa too. There's a bit of everything. That's it. And France is very good at this. France has a culture of what we call geochemistry, which was born here with the renowned scientist Mr. Allègre, who was involved in politics and much more. But throughout his sphere, he developed expertise in France and we became very good. And I think at the time he worked heavily on the lunar mission since we had special ties with the Russians. And we know how to do it. It's something we're very at, geochemistry. And by the way, the day we have, the Martian samples right now, we're in the process of collecting them. The mission is called Perseverance. So the rover is named Perseverance. We, the French, used our small laser to give it the same tools, since that's our specialty. It's moving and has traveled over 35 kilometers. It's moving forward. So just today, it just woke up. You don't know this, but actually, we monitor the rovers every day, except for 3 weeks every 2 years. 3 weeks every 2 years, it gets a vacation, us too, which is great. This year it was during Christmas. Why? Because we're in conjunction. There's Earth, the Sun, and Mars. We're aligned, so we stopped communicating with them. That happens every 2 years. Today we got data confirming both rovers, including Curiosity, are fine. They got through the conjunction just fine, so we're going to take control again. And so every day we operate it, we say, hey, that rock looks interesting. Cameras often decide where to go, guided by your eyes, just like us. Once we arrive, we put the hand down, scrape, and shoot with the laser. Another one does some measurements of what we call Raman. Another one does some measurements, some complicated chemical measurements, an absolutely amazing instrument called Pixel. So each one does its own measurements. Then we suggest bringing one back to Earth. We remove the arm, use a corer, put the sample in a tube, seal it, and place the tube. We've already made more than 30 tubes like that.
Okay.
And each time we take 10 grams. So we're a little bit afraid that the rover might break down and the tubes could get stuck inside. That would be a bit silly. So we dropped 10 on the ground in one place. 2 years ago, we put 10 on the ground. That's what we call the backup in case we break down. And if everything goes well, we'll keep taking more. We have 10, 20, either way, we'll have 30. We'll keep collecting them and wait for someone to pick them up. Right now, the United States, we're building a system to land, but more importantly, to take off again. People often forget that those 250 famous probes I mentioned are all one-way trips. We only return when bringing astronauts back because we like them or when we need samples. But all our vehicles, they're still over there. There are a few wrecks on the moon and quite a lot on Mars. Nothing ever returns. The Americans were preparing a vehicle to land next to us. So we're there, we're driving, we're talking about 2030, 2032 or so. Around that time, the vehicle is next to us and it comes with not much, just a rocket. The rocket stands upright. We have our samples, our 30 samples. 30 times 10 grams, that's only 300 grams. It's not a lot. And as I told you, 10 milligrams is enough. So that's a lot of samples for labs all over the world. We give it to them in the rocket, which takes off and carries a basketball-like object that it puts into orbit around Mars. There, a vehicle arrives from Earth, which is currently being built in Toulouse, called Aero Earth Return Orbiter, something like that. It arrives around Mars, it tries to find the basketball, grabs it, which isn't easy, then leaves Mars, something we've never done before, and brings it back to Earth. That's called sample return, and we think we will have our samples around 2035. We learn patience.
Yeah.
That's just how it is. And honestly, things are complicated with the Americans right now.
Yes.
NASA, lost 20% of its staff. I think they'll recover. It's going to take years and years. They had almost all their projects canceled. And now, after seeing the budget, everything was approved. As usual, they make promises but don't act, except for the sample return, which was also canceled. We learned about this a week ago, so we keep preparing our samples, hoping someone will follow through. We've learned patience, we've learned to deal with political upheavals. Perhaps rightly so. The program might have been poorly designed, too costly, or lacked credibility. It's up to us, the Americans and the Europeans, to work as well. There may be some frustration, especially we're very close to politicians, as I said. But we believe in it, we need those samples. There's a little thing that's going to save us. We've already talked about the Chinese. And the Chinese, they said, yes, we're also going to do a sample return from Mars, a bit like they did from the moon. I think they'll land, collect a sample, and return. It may not be as valuable as the 30 samples we chose, but we're considering it. Every time we take one, we drive, we say, hey, we don't have this one yet, or we already have this one. Maybe they'll do something quicker. They might be the first to return a Mars sample. Maybe that'll save us, since it'll annoy the Americans. We're kind of in between. We like to play on both sides. We've historically played with the Americans, and we've also played with the Soviets for a very long time. The Toulouse company was the main focus. And we're playing with the Chinese more and more. I mean, we're participating, we're collaborating, and I'd like us to do it even more. There's a bit of politics involved. Of course, we collaborate a lot with the Japanese. The Japanese have decided to make another comeback. They're good at sample returns with their 2 Hayabusa missions. It's called MMX, and it's leaving this year for Mars to bring back samples from Phobos, one of Mars's 2 moons. Mars has 2 small moons, and they said, well, it's complicated to do it from Mars. There's strong gravity to take off again, but taking off from Phobos isn't complicated. You just do it. You take off. There's practically no gravity. In fact, it's even difficult to... IDEFIX is a small rover built by CNES and the German Space Agency. They struggle to stay grounded. They say, we avoid sudden moves because we are going to take off, so they will try to crawl slowly. It'll be amazing. The Japanese said they'd bring back a sample from Phobos. So this obsession with bringing back samples, I think you understand it, because we know how to do great things in our laboratories. Mars, we're going to be years behind on that. Will I see it in my lifetime? I hope so. But when you see how hard it is to bring back 300 grams, we haven't even sent astronauts yet.
It's not happening soon.
Yeah, it's not happening anytime soon. But we know that we call them the treasures of humanity. I think it's extraordinary, these samples. And all the nations that have had them have shared them. There's a real convergence here. At some point, we need to stop focusing on politics.
Earlier, we mentioned Venus, saying it's not happening soon because it's even more complicated. Why do we want to collect samples from Venus, and why is it much more complicated?
Well, Venus, if I have to analyze my career, it's my biggest regret. It's missing out on Venus.
All right.
I took part in quite a few proposals. You know, for us, it's a pretty competitive field, meaning we're constantly competing with each other. Collaboration and competition together make our work strong. And there are calls for tenders saying, who wants to do a mission, $1 billion mission? Do you have any ideas? And several times I took part in missions to land a vehicle on Venus, and I never succeeded. We never managed to get through. Only the Soviets did it with the Venera missions. But, you know, Venus on the surface, well, Venus. Many believe Mars is Earth's twin planet, but it's actually Venus. We like Venus. You see it in the sky since it's inside Earth's orbit. You'll see it at sunset or sunrise. Make a little drawing. Obviously, you're going to call it the Shepherd's Star. And this Shepherd's Star, well, it fascinates us. It's practically the size of Earth. But on the surface, it's 450 degrees. And the pressure is 90 bars, 90 times the mass of Earth's atmosphere. It's impressive, and it's hotter than a pyrolysis oven. And getting there is a nightmare. The Soviets did it, and it was their big success. They failed on Mars and had successes on the Moon, but missed the hardest part, landing astronauts, and ultimately didn't finish the mission. Venus, they succeeded in all missions. The Americans never landed but made impressive orbiters like Magellan. And then Venus, which interested everyone in the 80s, was abandoned. For 30 years, we had hardly any missions, only a few occasional ones. The Japanese tried with the Akatsuki mission and the Europeans with the Venus Express mission, but nothing really big. 4 or 5 years ago, we chose 3 consecutive Venus missions, all orbiters, because landers are considered too complex and hot to operate there. For our projects, no matter how much we brainstormed or consulted engineers, they'd say landing isn't that complicated. It's so dense, it's almost just falling. It's not like wax, but in a liquid. No, it's a gas, the atmosphere, with a density of 0.1. It's practically not a liquid, but it's so dense. On Venus, if you fall with arms outstretched, it takes about an hour to reach the ground. You pass through a pleasant area at 50 kilometers with 1 bar and 25 degrees, just like Earth. It's acid, so not great. Then near the surface, it's 400 degrees. So your vehicle, it only heats up and can't cool down. And so every time we designed a mission, we couldn't survive for more than 2 hours for now because we don't know how to cool down. Some people say 1 billion for 2 hours is complicated. The Soviets did it, but their missions lasted less than 2 hours. They flew several missions, more than 6, but not all succeeded. Each time they went further, stayed longer, and achieved great successes due to Venus's many fascinating questions. We always return to our earthly problems, the greenhouse effect, a massive and ongoing issue. We complain about our 3 degrees, and we're right, because things aren't going well and we'll have to address these issues. On Venus, we're talking about 300 degrees, 400 degrees of greenhouse effect. So that's real greenhouse effect. It's interesting to study that. It's interesting to try to understand, was there ever an ocean on Venus? We have one ourselves. Our ocean isn't huge, but on the surface it covers a lot. So we have plenty of great questions about Venus. We need to visit the surface, but we're achieving plenty from orbit. We've relaunched a mission called Envision and 2 American missions called Veritas and Da Vinci. And Da Vinci, by the way, will enter the atmosphere, but it's mainly the atmospheric profile that interests us. Envision and Veritas are more about radar. A world, so here you see, it's a world covered in craters, impact craters, no atmosphere, nothing. Well, Venus is a world covered in volcanoes. It's nothing but volcanoes. There's a continent, what we call a continent. It's a bit higher. There are terrors, arachnoids. There are lots and lots of things with strange names. It goes in all directions. It's quite something. It's a zoology of Venus with many great questions. How can a world derive like that? In the sense that it went off the rails like Venus. I missed Venus, I would have liked to, but that's how it is. You can't do everything.
Wall, yes. Of all the planets you've studied, and more broadly, of all we've been able to study, what has it taught us, actually? What are the conclusions that...
We're nearing the end. People often ask me, after 25 or 30 years exploring the solar system, what have you learned? So your question is, what's the most fascinating planet? Well, it's Earth. Let's not kid ourselves what we've learned from... For me, it's been 25, 30 years. But for the previous generation, it was another 25 years. So we're almost at 60 years of solar system exploration. So we're starting to get good at it. We've learned about Earth. And maybe that's the first lesson. It's that we've discovered Earth is an extraordinarily rich planet. Because of its large size, it still has a working dynamo, which maintains its magnetic field, atmosphere, and surface liquid water. It has preserved the concept of duration. Mars didn't survive. After 1 billion years, it spun out of control. Venus did too, but we don't know much. Earth is the right size and distance from the sun, which is exactly why we're here. It's a new way of seeing our existence. And what we've learned from all this exploration of the solar system is that there isn't a second Earth. There aren't any others. I went back over what happened. In the 70s, you know, after the moon, people said, by the year 2000, we'll be living on the moon, we'll be living on Mars. No, still not. It's difficult. Some people thought that Mars after the moon was the future of humanity. So first we learned our planet is unique. There's no plan B in the solar system. Especially now, it's important to remember that. Those who say we're going to go to Mars, well, we won't start another show to debate it for too long, whether we should send astronauts and so on. But for exploration, yes, for scientific reasons, for the sake of humanity, our civilization explores, yes, but not to save ourselves. So maybe that's the first lesson. What I've learned is that, well, the future of mankind is it's Earth. It's funny how we always carry those little phrases that stick with us. That one from Tchaikovsky, who is the father of astronautics, who said, the Earth is the cradle of humanity, something like that. We're not meant to live in our cradle. Well, yes, what I've learned is, yes, we are. Now, that doesn't stop us from going to explore elsewhere. Exploring helped us discover Venus's volcanism, which taught me about various types of terrestrial volcanism. We discussed how Mars once had a greenhouse effect that allowed liquid water, but it disappeared, so now Mars has no liquid water. Or the greenhouse effect on Venus, or the ozone layer, which is interesting. There is no ozone layer on Mars, but there is one elsewhere. Or the auroras or tidal effects. You know, we have a tidal effect between the Earth and the Moon. There are incredible tidal effects between Europa, Ganymede, and Callisto around Jupiter. I feel like I'm discovering a little bit of Earth everywhere. A bit of Earth's history and a glimpse of what it could become. So in the end, I think that's kind of our role too. Obviously, we can't say that one science is more important than the others. That would be too dangerous. But it's true that right now, everything related to the environment has to be a priority. We're all aware of that. It's becoming critical. We, as scientists, can't ignore the problem, and we don't ignore it. We have to tackle it in our own way. So we astronomers, we're a bit removed. We're the first ones who go out as soon as well, space is important for the planet. The well-known measurements from the Intergovernmental Panel on Climate Change, as you've seen, are taken by satellites. We need satellites, even though launching a rocket pollutes a bit. Not all of them, but yes, of course it pollutes, especially when the pieces come back and so on. But we need space. Do we need exploration? Well, yes, it's a bit like, when you step out of a system. There's something that impresses me. Often when we're on Mars, we say, hey, let's take a measurement. I measure my little rock over there. I dig, I do this and that. Then at some point in the plan, it would be nice to take a picture of Earth. Right, let's take a picture of Earth. Actually, it makes us feel good. So often you'll see there are beautiful pictures of Earth. It's a dot. But you know that from there we can't see it well right now, but we can't see it at all right now. From Earth we can see Mars, so there's no reason why from Mars we couldn't see Earth. We also remember that I talked at the very beginning about the Apollo missions, the ones that leave the solar system, and there was that famous family photo. They said, well, the probe, not Apollo, excuse me, Voyager, the Voyager 2 probe had just passed near Neptune. They say, turn around and take the family photo, so there's the family portrait. You see all the planets and one tiny spot called the pale blue dot. That is, there was a very beautiful text written by Saga which says that everything you love, everything you know, lives on that little dot. It's a bit scary. It's like a little dot in the universe, in the void. It's a kind of vessel. And I think you become aware from space of this rather unique aspect of the Earth. Just like the Apollo 8 mission. And we have to talk about Apollo 8 because Apollo 8 was the mission that orbited the moon. You go around and come back. Jim Lovell did that and he just passed away. He did Apollo 13 afterwards. Well, anyway. He completed the Apollo 8 mission and will do it again. It's called Artemis 2. We did it this year, and in 2 months we should repeat the Apollo 8 mission. And this very beautiful photo from Apollo 8, where we see the moon and then we see the Earth. So we called it Earthrise, which is a bit strange because it's not really the Earth that's rising. It's the relative movement. And when people ask what it is, well, we always have fun calling it one of the greatest photos of the century. This one is one of the greatest photos of the 20th century. We called it humanity's ecological awakening. It was by seeing the Earth from the outside that we realized it was a whole. Call it Gaia or anything else, the Earth is alive with people and all resources on it. Imagine that one day we'll go get ice from a comet. If it comes to that, I think we don't deserve it. We need to stop the business. We brought back materials, iron. In the end, none of this really makes much sense. Maybe we'll do some mining, get things from the moon for a lunar base, but bringing it back to Earth, in my opinion, we don't deserve our title as living beings of the galaxy. I mean, what's interesting is this perspective. The astronauts call it the overview effect. They all come back from space saying, I saw an Earth. There are no borders, it changes. I saw it in its beauty, in its changes. I saw the northern lights. I saw northern lights on Jupiter. I remember it was at the beginning when I was doing this. It's amazing, the northern lights on Jupiter, the northern lights on Mars. They're completely different. We just made a very good measurement of a green aurora. Today we have auroras. Tonight there's an aurora that's going to come very, very far south in France. We know how to predict them. So there's the answer to your question. I think what we've found the most in the solar system is on Earth. Well, that's a bit presumptuous. It's like saying man is the center of everything, which is somewhat true. Well, it's kind of true that we're at the center of everything. I don't know, but that's kind of what we think. But in any case, in this great movement that's making everyone aware of the uniqueness of the Earth, as astrophysicists, not just planetologists, we also contribute. Similarly, if I think about my colleagues who do astronomy like me, but whose messenger is simply not vehicles like us, we're very lucky, but rather the photon. They study exoplanets, which orbit stars beyond our solar system. There they find both Earth-like and non-Earth-like planets. They find Jupiters instead of Mercury and ask, why isn't our Jupiter where Mercury is? Earth shouldn't exist then. So they rethink models and look for other systems. Because actually, the big flaw is kind of thinking like someone who wants to make a digital model of the solar system. Then they'll tweak the settings so much that in the end, there are 8 planets, 4 big ones, 4 small ones. There are many possible solutions, but some aren't. And then when we look at all the solutions, we realize we've actually been pretty lucky. We realize Jupiter could have gone through everything and swallowed us up. That happens often. Fortunately, it was kind of caught by the skin of its back by Saturn. We realized that we could have, when we go around the galaxy in 260 million years, we could have gone through, passed by a supernova that would have wiped everyone out, or some kind of cloud or something. Some people mentioned luck or destiny. It's true that we really, really were lucky, but that's just looking back, because if we hadn't been lucky, we wouldn't be here to say we were. I think something like that exists. I can't recall the name, but exploring the solar system has a cost. It has a financial cost. It has a cost. It creates reasonable technologies. It creates excitement. We talked about young people. Thanks to you, it's going to inspire vocations. So they all want to be astronauts. It's okay. They won't all become one. Unfortunately, there aren't many. We wish good luck to Sophie, who's about to take off. By wanting to be astronauts, they aim to work in space or technology in general. It's a great motivation. This space inspires us and lets us view the Earth. These are messages to share. That's kind of our thing.
Okay, thank you very much for this interview, which was extremely interesting.